Good morning.
Hey, good morning.
All right, we get to look at a little bit more of the equation of a plane. Cool. So we learned yesterday that the equation of a plane is oddly defined kind of by the line that's perpendicular to it, which is kind of cool. I am very interested, even though it's something you're going to see in the book, that you see the connection between that and what you already know. In this sense, I guess I'll just say this is 13.5 continued. In the sense that if I gave you some equation like 5x plus 2y equals, let's say 20, that the vector 5, 2 would also be perpendicular to the line. And I think you can see from yesterday that that's a direct consequence of the fact that the slope is found by subtracting 5x from both sides and then dividing by 2. And so the numbers, when the line is in its what's called standard form, that 5, 2 would kind of by nature be perpendicular to that line. And so when we bump it up to our world where we say 5x plus whatever 3y plus 2z, what are you doing that? Plus 2z equals, let's see, all those go into 30. That for the same exact reason, 5, 3, 2 would also be perpendicular to the plane. And so it's just extremely cool that these shapes are kind of defined entirely by, well, those coefficients right there. And we saw yesterday that the 5, 3, 2 really affected, what angle the plane was at. Whereas the 30 just kind of told us where it was vertically. It didn't change its orientation or its slope. And as I mentioned yesterday, the slope is a little bit not a perfectly clear word in 3 dimensions. It's perfectly clear in 2 dimensions, but in 3, slope is a little bit dependent on which direction you're walking. And so that's kind of interesting. You'll get into something in Calc 4 called a gradient, which is where you say, I'm interested in the steepest slope. If that's the case, then you can talk about the slope of a flat surface, and then you're talking about the steepest slope, the steepest climb you would make. So let's see, with respect to that angle concept, why don't we just tackle that as an example first? What if I gave you a couple of planes? An example, find the angle between a couple of planes. This is rather beautiful. Between 2 planes. Remember, if you have 2 lines, there may not be an angle between them because they could be parallel. But if they don't have the same slope, then they're going to hit somewhere, in which case there'd be an angle between them. And I guess it would make sense that planes would be the same. They could possibly be parallel to each other, have the same slope. But notice that would be utterly apparent by just looking at these numbers right here. I mean, they'd have to see them as exactly the same set of numbers. Well, then of course there's not going to be an angle, but again, that represents kind of an anomaly. So if I just make this up for random, why not reuse this guy since I already wrote it? And we'll just make another one. And again, I want to give you a second to think about this. So, and 2x plus 4y minus maybe 1z. Again, it's always kind of nice if these all go into the same number. Like, these are pretty graphable. Would you agree with that? Because since all of the coefficients go in, as a for instance, if I pick x to be 6 up here from yesterday, then y and z could be 0 and it would be equal to 30. So there's a point on the graph. We said yesterday it takes 3 of those. And so I could graph these, which is nice, if you will, since all the 5, the 3, and the 2 all go into 30 evenly. I could graph this pretty easily by hand. But you can tell they don't have the same slope because 5, 3, 2 is not a scalar multiple of 2, 4, negative 1. So these are definitely going to run into each other somewhere. And, you might have this vague recollection from our note sheet. At least when we're in 2 dimensions, we had a kind of a formula for this, that the cosine of the angle was equal to the 2 vectors. In this case, it was vectors, right? It was like vector u dotted with vector v divided by their magnitudes. But those are vectors, not planes, right? So, maybe that feels like it's not going to be useful here. But here's the thing that's really cool. Let's see, do I dare attempt to draw this? Given that a plane is defined by its perpendicular vector, if I just draw one kind of randomly, again, it's kind of typical to draw a plane as being kind of like a parallelogram. Does it make sense its vector that takes off from that perpendicular to the plane? Does that look perpendicular? Again, it's kind of cool if you go like this so that you can see that that vector actually goes in both directions. So, this might be the vector 5, 3, 2 kind of going off in that direction. So that's really the only vector we have. And so, what I'm finding myself wondering as we think about this, is there some way to use that? In other words, these over here were vectors, right? So just going to give you a second to think about that. Is there some way to use that fact? Like, I'm thinking about the angle between the planes, but in the end, we saw that there's a lot of cool things I can do with vectors. And so could I maybe consider the vector 5, 3, 2, even though that's not the plane? So some way I could use that. Just want to give you a second to think about that. I'm going to attempt to draw this as though these planes intersect each other. Let's see, does that look right? This would be above it. That red one would begin to be dotted. Just play with this. I'm just playing while you have a chance to think about this. So does that look like 2 planes intersecting? Because you watched me draw it, perhaps you at least see that it's roughly the case.
You're good at that.
It's not terrible. Well, let's move this down to the end. So here's actually the line where they intersect each other. So of course, we're kind of looking for this angle right here. So if there was a way to kind of consider these 2 vectors, if you will, as kind of u and v, like that'd be cool, right? Because then I could just use this formula up here. But remember, I'm drawing that, I'm drawing those as like rectangles running into each other, but they go forever. So does it make sense that u and v vector, it's not like they're on the side of this rectangle, they're just in there somewhere, they're in some random location. So that'd be kind of hard. But think about this, and this is, again, I think rather brilliant. what if I drew the perpendicular vectors to these? Like, isn't this, if I draw that vector as kind of the perpendicular vector of the, well, the red one? In other words, that's the vector 2, 4, -1, which I should draw as a vector symbol. So that's not one of the vectors. But what do you notice about if I draw the other perpendicular vector as well? Kind of the green one, so that it's perpendicular to that. And so now it's not as easy to see. Maybe I'll come back over here and draw that 90 over there, just so it isn't quite so weird. Go and erase a little of it. Again, I'm just trying to give you time to think. That was a bad decision.
Is it the same angle as the obtuse angle?
Yeah, do you think it's the same? That's kind of the question.
Yeah, I think they probably are, because those are both 90 degrees off from each other, so they're the same amount different from each other, I guess.
Yeah, that's exactly right. Your intuition about that is exactly right on. If the two planes have some angle between them, theta, then both of those perpendicular vectors are rotating 90 degrees. They're both rotating 90 degrees. And so does it make sense that they'd actually be the same angle? So again, my drawing is not great there. Probably, sorry, I see my screen just went blank, which I just thought this today that it was kind of come back in a second. You guys still see my screen now, but you just don't see me. Is that what you see when that happens?
I see a black screen and your camera's lagging. It's going a little bit slow. I think the camera fixed now. Still a black screen though.
Yeah, both. I have two monitors, my regular laptop monitor and the kind of a second monitor, and both of them are asleep. I wonder, usually it kind of wakes up a little faster than this. Anyway, yeah, it actually turns out that those two angles are the same. And so this formula that we have to find the angle between a couple of vectors can be used here entirely just based on the two normal vectors. And remember, this over here, I'll call this normal vector 1, and I'll call this one normal vector 2, just since they're both normal vectors. So normal, what's the other, you guys know all your words. What's the other mathematical word for 90 degrees besides normal? Perpendicular is actually another one, but does anybody know yet even another one? Because I think I see this in your assignment, so it's kind of good for me to mention.
Complementary?
Actually, that's even a fourth. Complementary is close, two angles that add up to 90 degrees. So it's still kind of in that 90-degree world. And the other one I was thinking of that shows up in your assignment is orthogonal. Have you heard that one before? I don't know why mathematicians and educated people feel the need to come up with so many different names, but so anyway, so this formula is actually going to work just the same. All I got to do is play with these two normal vectors and just do what we did in the past with them. So let's see, the question is, does it still work the same for something in 3D? And so the answer is, well, yeah, it does. And so if I dot product those two vectors, normal 1 dotted with normal 2, if you have a GeoGebra, you might actually graph both of these planes in GeoGebra and see if you kind of visually can agree with this answer we're about to get. So let's see, if I dot those two, I'd have 5 times 2, which is 10, plus 3 times 4, which is 12, plus 2 times -1, which is -2. So I get 20, 22 and -2, I get 20 for the top. And then gotta find both of their magnitudes and multiply them together. So for N1, I get 25 and 9, which is 34, and 4 more, which is 38. So I think I get the square root of 38. Just try to do this quickly in my head. And then 4 and 16 is 20, and 1 more is 21. So I get those two sizes, and ultimately that doesn't really change. And if I just take the inverse cosine of that answer, whatever it is, then I'm getting the angle between them. So that's kind of cool. Since I made this up, I don't have any choice but to go ask it what is the answer. As I mentioned to you the other day, the faster way to type this is to say 20 divided by the square root of 38, not times, but continue with divided by. Then you don't have to put extra parentheses in there if you're lazy like me. I got 44.9 degrees for that. So that's kind of cool because it's almost 45-degree angle. So that should be a little more apparent, easy. It should look like it's half of 90 degrees then. Hence theta.
I had a question.
9 degrees. Go ahead.
Can I draw on here real quick?
Yes. Let me see. Do I have
Just wondering if this angle is the same as this angle.
No. So if you have two lines that intersect like this, there's going to be one angle over here that's 45, and the other angle on the other side would be supplementary. In other words, they have to add up to 180 because they're a straight line.
Mm-hmm.
So there's really only one angle that defines the intersection of two lines and two planes. So you only need to know one to know all of the rest of them. But basically this angle over here is going to be the 45, and this one over here would be 135. And based on the way I drew that, you can't exactly tell what size those really are because you're sort of pretending you're seeing 3D.
Okay.
Yeah, that's a good question. So I won't take the time to draw it, but it's kind of tempting to do so. So that's kind of cool. In a sense, we didn't actually have to learn anything new, but it's just kind of interesting that we don't actually find the angle between the planes. We're finding the angle between their perpendicular representatives, if you will. So since they're both rotated by 90 degrees, then angles would be a match. So that's kind of cool. And since we're staring at those two examples, let me give you or two sample. Let me give you another question that's kind of related and give you a little bit of time to think about it. Could you find, you remember in kind of line land, we said, hey, look, you got a line here and you got a line here. Let's see if we can find the equation, I'm sorry, the coordinates of their of a point, their intersection. So I'm going to find out where they intersect, and they're going to intersect in a point. But of course, if we intersect two planes, as the drawing above shows, they're not going to intersect in a point. They're going to intersect in a line. So the black line that I drew up above. So let's see if we can figure that out. What would that equation be? And it's also kind of interesting to think it, again, by pattern, for those of you that either are or will someday take linear algebra, by pattern, a line is a two-dimensional shape. And so two-dimensional shapes intersect at something that's one dimension below them. So they intersect in a one-dimensional shape. Two planes, a plane is a two-dimensional shape. Did I say that right? Two. Actually, I said that wrong. This is really a one-dimensional shape. A line is one-dimensional, and they intersect in something that's no dimensional. Whereas a plane is two-dimensional. I mean, you could think of it as three since it exists in a three-dimensional plane. So a two-dimensional plane intersects in something that's one dimension below that, something one-dimensional, a line. So by pattern, it's kind of cool to think about this. And again, the interesting thing about linear algebra is this logic works on into 4, 5, 6, 7 dimensions. The math remains the same. It's just that we kind of lose the capacity to visualize it. But I wonder what the equation of that line would be. Could we find the, whoa, could we find the equation of the line? I want to give you a second to think about that. I think I'll go graph these. I'll go graph these two planes really quick just so we can kind of stare at it while I give you a second to think about it, because I'd like you not to ultimately see these questions as quite as formulaic. You'll notice if you struggle in this section that the problems I linked, almost all of them come with a video. So worst case scenario, you can watch the boring video and kind of learn how to get the problem right real formulaically, but that takes all the fun out of it. You know, the question is, could you play around with this some and make any progress with it without anybody telling you what to do? So I'm going to give you just a minute to consider that. Five, 3, 2, 30. So we can see visually that they intersect in a line, and that's kind of cool. And we can also see, if you didn't do this before, that 45 degrees for the angle between them looks pretty reasonable. If I just turn it just so. You may notice I hit those little 3 dots just to the right of the equation, because they, instead of having the sense that Desmos does to say, well, they just made 2 planes, why make them the same exact color? GeoGebra, they come out the same color. So I hit those 3 dots and just made that second one a different color. I can also go in, I don't think I'm going to do it, but I can go in and turn off. Now that I actually have 2 planes here, I could go in and turn off the floor. Notice it's kind of built with a floor for the XY plane. I could turn that off and maybe that'd be helpful. But clearly there's a line. The question is just, what is it? So this is good review for yesterday. In this sense that we, like, what does it take to make a line? Like, what does the equation of a line look like? So what do you need to know from yesterday to find the equation of a line? What's the ingredients? What do I have to find out? So I can go in here and kind of sketch that line in, noting that it's going to keep on going, and then also noting that in 3 dimensions, that drawing is almost not helpful. So from yesterday, what does it take to make the equation of a line? Equation of a line, it's really going to take a point and a vector. In other words, 1 point, and then what direction are you going from that point? That's what we saw yesterday. I got to know some point and then some direction. So Is there a way to find a point? I mean, let's just start with that. Is there a way you could find a point where two planes intersect? They intersect in a whole bunch of points. Is there any way you could find one of them? It's an interesting question.
Could you set them equal to each other and end up with an expression that represents where they intersect?
Yeah, think about this. Isn't it kind of analogous to, you know, what you did for a line? If you have two lines, what did we actually do with two lines? I mean, if I said this equation right here was 3x plus 2y equals 6, and this equation over here was 2x minus 5y equals 10 or something like that. What did we do to find that point of intersection? We did make them talk to each other. But it's not so much that we set them equal, although that's kind of true. What are your thoughts?
If you solve for one of the variables, then you can, yeah, when they're both solved for y, you can set them equal, but otherwise you could substitute one variable in for another, or do elimination or something, just solving that system of equations.
Yeah, the larger picture key is, as Cheyenne said, if you solve them both for, say, y, then you could set them equal to each other. But as Ben pointed out, to save a little time, I think that was Ben, you could just solve one of them for y and then plug what y is equal to, which would be a bunch of numbers and x's, plug it into the other equation for y. But the end result of that is, by putting them together, instead of two equations, two unknowns, you'd have one equation, one unknown. And then the answer to that one equation, one unknown, because it came from both of them being put together, would be one of the answers you had here. And so, you know, one of the classic ways to do this, as a reminder, is if I took 2x minus 5y equals 10 and 3x plus 2y equals 6, is to eliminate a variable by not working so hard, because the problem is, if I solve for y or for x, I'm going to get this bunch of ugly fractions. But perhaps you remember that I could take this entire equation, since it's okay to multiply it, well, by a scalar multiple. If I multiply this one by 2 and this one by 5, perhaps you can picture why I said that, then I would have negative 10y and positive 10y, which means I could add the two equations together. And I think you're good enough at algebra that you can see this, but if I took 2 times 2x, which is 4x, and 5 times 3x, which is 15x, when I added 4x and 15x, I'd get 19x. When I added negative 10y and 10y, I'd get no y's whatsoever. And then when I added 20 and 30, I'd get 50. Notice I made that up randomly, and therefore the one equation, one unknown, I just reduced that to. I just did that in the easiest way possible. That's actually easier than substitution. And that's what you study in linear algebra, except you just take it to the next level. So notice I got a pretty ugly answer for x. This was in the canned book problem. I got 50 over 19. It doesn't reduce to some nice clean number. And so what I found is the x coordinate of this point. But can you see that there's going to be some problems for us if we try to do that? Why is that going to be harder? What's kind of worse about what I have here, more than just they're bigger?
Well,
can I do the same thing?
You have three variables, so you can't, like, when we solve for y up top, or when we solve for x, we immediately can find y and figure out the point. But there's too many variables to just do that.
That's exactly right. If I did the same thing I just did, I could choose to multiply. Let's get rid of z just to make it easy. I could choose to multiply this one by 2, which means that'd be negative 2z, which already matches the green one, so I don't have to do anything to the green one. But if I add those, does it make sense I'm still going to have x's and y's? And so the question is, like, is that fruitful at all? Does that do me any good? I'm not just going to get a point. Well, maybe that's good that we don't get a point, because these two planes don't intersect at a point. They intersect at a whole bunch of points. But let me show you kind of a cool way out of this. And that is this: since that line goes forever, does it make sense that that line takes on all kinds of answers? In other words, in this example up here, we just found out x needed to be 50 over 19. So can x ever be 2? Well, no. But in our problem, can x be 2? Yeah, there is some point on that graph where x is 2. It goes forever in every direction. Could x also be 3? Could x also be 5? Yeah, there's actually all kinds of answers. And so in the process of solving these, or trying to find at least one point, find one point, couldn't I just let x be, and I'm picking x at random, I could be picking y, and I'll let it be anything I want, but I'm lazy, so I'm going to pick x to be 0. But you can pick x to be 4 or anything you want. And again, I made these up randomly, so it's probably isn't going to come out really nice. But notice if you let x be 0, then that means our green equation turns into 3y plus 2z equals 30. And our red equation turns into 4y minus z equals 16. And so since I chose x to be 0, perhaps you recognize that with that limitation, then there's only one point that's going to work. And notice that reduced it to 2 equations, 2 unknowns. And so now I can continue to get the rest of those unknowns. And so again, as I mentioned a second ago, if I multiplied this one by 2 and added them, I'd have 3 plus 3y plus 8y, which is 11y. That's not a good sign. 2z plus negative 2z is gone. And 30 and 32 is 64, and we did not get lucky in the sense that our answer kind of came out sort of weird. And so y is equal to 64 over 11, which is going to make our process maybe not so fun here. By the way, like, is there some other choice? Could I have made up a problem where these came out as whole numbers? Absolutely, I could have done that. But I would have had to work at it a little bit. So now that we know what y is, does it make sense we could go back and figure out what z is? So let's see, it looks like it doesn't really matter. So I'll use the top equation. So 3 times y that we now know is this, I'm substituting this in, equals 30. So I'm just going to get my calculator out and say 30 minus 3 parentheses 64 divided by 11. Say answer, get somewhere decimal, divide by 2, get somewhere decimal. Ask my calculator to convert that to a fraction for me. I got 69 over 11. So z is 69 over 11. And so I actually found a point. 0, 64 over 11, 69 over 11. There's a point that's on that graph. So I found a point. How am I going to get a vector? What does it take to make a vector? Again, I'm interested in you thinking here. I'm going to show you a crazy shortcut in a second for this. We're just kind of trying to get this old school or blunt force. Doesn't it take 2 points to define a vector? Like, don't I have to have 1 point here to represent kind of the start of it? And then if I want to know, it goes over there, no, it goes over here. Like, don't I have to have a second point? So if I had a second point, then wouldn't I be able to find a vector? So now I got to go find another point. So the only thing that's important then is just don't pick x as 0 again. Like, pick x as something else. Pick x as 2, or switch to some other letter. Pick y as 0. Doesn't make any difference. Just pick something. I just got to find 2 points that work. So I don't know. Second point. I'm going to I'm gonna let y be equal to 0 this time and hope for better things. And so if that's the case, if y is 0, then don't I get 5x plus 2z equals 30? If y is 0, don't I get 2x minus z equals 16?
For
So I'm
that,
gonna take, I blew it.
oh, for the 11y equals 64, I got 11y equals 62. I think because as we multiply that 16 by 2 to be 32, and then add the 30, I think.
32, oh, good job. That would have been no fun.
It's close.
62, so I'll just quickly fix that. So if I say 3 times 62, that's a bummer. Still going to be kind of an ugly answer, but at least it'll be the right answer. Thank you for pointing that out. So I got 72 over 11. I'll leave the evidence of my foolishness there in a different color. So let's try to get this right this time. So I'll take the same approach, multiply this by 2. So I have 5x plus 4x, which is 9x. I have 2z and negative 2z, which is gone. I have 32 and 30, which is 62. So x is 62 over 9. And so that means that z, if I add it to the other side, would be equal to 16 plus 2x. So 16 plus 2 times 62 divided by 9, big ugly decimal. Turn that into a fraction. I get, whoa, is that really true? Seems wrong. Is it wrong? 2x. No, I guess not. 268 over 9. So if I give a question like this on a test, either there must be some easier way to do this, or it would be sure nice if I took the time to make up a problem where these came out whole numbers, but it doesn't mean that you can't do it. It just isn't going to kind of feel as satisfying. And I'll leave this for you to think about, but let's put yourself in my shoes, you future teachers. How would you make one up that would come out with whole numbers? Would you be able to do that? How hard is that to do? So now I have these 2 points. So how do I get a vector? So if I kind of choose this as my first point, so I have 2 points now that define this line. I know both of these points are actually on that black line that we drew earlier. I know they're on there. Now I just got to make an equation of a line out of them. So if I call this one my first point, how do I make a vector? How do I make a vector out of 2 points? Maybe I'll call this one A and this one B. Somebody put it into words. What do I do? How do I get vector AB?
You subtract b from a.
Yep, subtract b from a. So 62 over 9 minus 0. Fortunately, that was easy. And then 0 minus 62 over 11. Fortunately, that was easy. And then this last one's going to be horrible, right? 268 over 9. Seems like I'm just going to get a crazy decimal for this, that maybe it'll have a denominator of 72. So 268 over 9 minus 72 over 11. Some crazy decimal, convert it to a fraction. Sure enough.
Wait, will
9.
the in front of be negative? The 62 over 11, would that be negative?
Let's see. Yeah, it would be. Thank you. Good job, because we're subtracting b minus a, so that'd be negative. And 268 over 9, since 9 and 11 have nothing in common, the common denominator of 99 is Not that surprising, perhaps. And I ended up with 2300 over 99.
Doug, I'm a little confused how you got Z for the second point, because I got negative 20 over 9.
I hope you're right. And then I've made yet my third mistake. Oh, yeah, I did make a mistake. So what I did was I moved Z over to this side and I moved 16 over, but I left it as a positive 16. It should have been negative. So now I get to fix yet my third dumb mistake. It's a bit of an embarrassing day. I shouldn't be making that many mistakes. I always like to say I want to make some just because it puts you at ease and helps you understand that people make this dumb mistakes. But so yeah, that should have been negative 20 over 9. So then when I subtract negative 20 over 9 minus 72 over 11, I'm going to get a different number. And that number I got was 868, negative 868 over 99. Apologize for all the dumb mistakes. So again, isn't that just super tedious? That, I mean, it's the very fact that the numbers are so crazy. And incidentally, like these are the kinds of mistakes I always make as a person because I get in too much of a hurry. So I just tried to mentally move 16 over the other side, and for some reason I didn't manage to think of that as a negative. So anyway, I think I've got it right now. So fortunately, what's the equation of the line then? Well, it's not that hard to write out now. It's really just A. So the line's equation is I start with some point, which unsatisfyingly was this. And I add to that, your book says, or we saw that GeoGebra likes to put lambda here, but just some number and then times the second one. I don't know about you, but especially given the fact that I made so many mistakes, I very much would like to graph this. And in my case, if I graphed it, I would have caught all three of my mistakes, but it would have caught me, it would, would have cost me hours, right, in order to catch all of those. And so that's unfortunate. So let's just satisfy ourselves again while you have a chance to kind of process this. And perhaps I even made yet a fourth mistake, but let's just hope not, because 3 is already too many. So I say, I have this point. I think we got away without naming this too. So I think I can just type the points in. So 0, and then it was 62 over 11. And then it was 72 over 11. Gosh. So I got to hit the right arrow key. I wasn't paying attention, but it was still down there in fraction mode. So I hit the right arrow key and then it jumps up for a spot for the next number. So I've got to hit the right arrow key again. Now I can close that parenthesis off. Then I say plus. So we're going to try this the other way. Remember yesterday I didn't do it this way. I just typed 0 plus 62 over 9t. I'm going to try to sort of type it the way they said. And so I'm curious if it'll let me put a t here. I mean, I wanted to have a t, right? So that's what I wrote. So will it let me? I don't know. My second fraction was 62 over 9. Arrow to the right, comma, negative 62 over 11. Arrow, comma, negative 868 over 99. So the question is, does it like this? Notice it does not like it. Isn't that interesting? Didn't like it. Unfortunately, I can't. Let me see if I can expand it to see what it says. It doesn't like to do this very much. I've noticed in.
I feel like last time it accepted it, but put lambda there.
Well, that's not what I typed last time. So I guess I'm going to, and I wanted to do this on purpose just so that we could learn something, but again, it feels like a little bit of a waste of time. But here's what I said last time. last time I said, okay, the x coordinate for the point is 0 plus the x coordinate for the vector, which was 62/9 times t. This is what I did last time. So we learned something. So there's my x coordinate collectively. So this is the parametric form of our points. So maybe there'd be some way to type what I just described, but it isn't simple anyway. Maybe I had to give it a name. I don't know. But it doesn't really make any difference. This is just as much time. So then the second point was 62/11. And then it was minus 62/11t. Is that really the same exact x coordinate? Yeah, I guess it was. Feels like we're taking too much time with this, but it's kind of satisfying to see it, I think. Sort of find myself wanting to see it. And then last one, 72 divided by 11. Move that to the right, say plus, except for I think it was minus. $868 divided by 99. Throw a t on that guy, and I think this is what it liked yesterday. So hopefully it'll like it again. Maybe the numbers are so big it won't like that either. So yeah, it liked that. Notice it turned everything into decimals, which is kind of interesting. But more importantly, oh good. Notice it really is the intersection. So this is also a good illustration for kind of how math works. In one respect, I don't think I taught you anything new there. I didn't in a sense. I mean, we were just learning this. So, I mean, I taught it to you new yesterday, but it's like all it takes to make a line is a point and a vector, or a point and another point from which we can make a vector. And so that's not that hard. And it was just relatively simple algebra that produced that. And I can pick any 2 points I want. I just chose some zeros to make my life a little bit easy. But the question is, you know, a mathematician says, that's great, but man, that sure stinks. Like, is there some way to automate that process? Is there anything I can do to kind of speed this up? And because I think it's neat, I'll show you another way to do this. Let's see, that example took up an entire page. So we kind of went back here, and I'm just going to kind of add to myself, or add a note for you. This is kind of the hard way. I mean, it wasn't hard mathematically, but it was very time consuming and so forth. But here's something interesting. If I took, I'll call this I guess I'll call this the easy way. But like, this is the kind of thing you would see in a book and do it, but not really maybe have any idea kind of what's going on or why it works. And I say easy way, maybe even in quotes, because I'm not really sure if this is going to be easy or not. But I'm curious to know if you can kind of answer this question. What am I getting if I take normal vector cross normal vector? What does a cross product produce?
Is it the vector perpendicular to those two?
Yeah, it's a vector perpendicular to those two. Why is that of interest? Why is that of interest to us? What good would that be? What would a vector perpendicular to both of those? What would that be in our picture up here? Where would that be facing? What should you think about that? while I do it. So I take 5, 3, 2, and I dot it with 2, 4. No, cross. Not dot. We're going to cross product that. And that was a little more involved than a dot product, right? It involved, let's see, it wasn't this, IJK, 5, 3, 2, 2, 4, -1. So again, I'm going to make the mistakes that I often make, which is go too fast here, but I'll try not to screw this up. So that'd be -3 minus 8, which would be -11. So my x coordinate of my cross product is -11. Then I do that again, except for 5 times -1 is -5 minus 4. -5 minus 4 is -9. But remember, you change the sign of that. So that would actually be +9. And last, if I cross out this row, then I get 5 times 4, which is 20, minus 6, which is 14. I don't have to do anything to that. So that's 14. So there, I found the cross product. And as I think I heard Cheyenne point out, this is perpendicular, right? It's perpendicular to those two vectors. If that's the case, which direction is it facing? I want you to try to divine that up. I will give you a little bit more time by graphing them. Let's see, I don't think I can call them N1 and N2. I think I'll just call them U and V. So U will be the vector 5, 3, 2. Maybe a picture is worth 1,000 words. So let's make one since we can.
Real quick, I think you have 15 there instead of 16 for your second plane. I've been writing down 16 in my notes. So did I get it wrong?
No, I think you are right. I think that was 16. I must have hit the button wrong. No, you're right. Which in my case was like a small enough typo that it probably didn't show in our picture. So we didn't see that. Hopefully that didn't make other mistakes. So notice those two, I didn't move those two vectors so that they're actually on the plane. It would be really nice if they were on their respective planes. Do you understand that? But the question is, maybe you can see it in this picture, in this angle right here. But if I go perpendicular to those two vectors, U and V, and notice because I just drew them sort of randomly, they emanated from 0, 0, 0. What's perpendicular to those two? Can you see it from that direction right there? If I cross product them, I get a vector perpendicular. You're forcing me to continue. -11, 9, 14. I'm going to graph that one too.
Perpendicular to the intersection line, right?
Exactly. What did I say that was? -11, 9, 14. Notice you, well, turn it on. Notice that it is pointing. I'm not sure why it's sort of so skinny relative to the other ones. But notice it's going in exactly the same direction as our intersection line. Do you see that now? How can that help us? What good is that? Well, isn't that effectively isn't that a nicer version of this right here? Like, didn't we need a vector that was going in the correct direction? And so that's what we did to find this. But that cross product gave us a vector that's going in the correct direction. Now, did you notice it wasn't in the right location? How do we get it in the right location? Well, just like we did a second ago, we got to find some point where they run into each other. We have to find a point where the two graphs run into each other. Now, in our case, we already did that with a couple of points earlier, but just for the heck of it, let's go find another one. So we now have, so I could sort of say about this cross product, if you like that mnemonic trick, this is like the correct direction. That's our direction vector. So second, since this is like the first thing we did, then second, we just need some point on the intersection to start our vector from. And of course, I could hope to find something that came out a little nicer, right? There may be a whole number on that line somewhere. Remember, there's nothing magic about picking X and Y as 0. I could pick X to be 12. Like, there's probably some kind of magic number that would make this work out really nice. And frankly, you just have to play with it to see what that number would be. But just to do it again, I'm going to quickly do this. And also because it's going to look different, I guess I'm just curious to see if you can see they're the same. So this time I'm going to let Z equal to 0, just because that's the only one I didn't pick before. So that means I'm trying to solve the equation 5x plus 3y equals 30 and 2x plus 4y equals 16. Maybe we'll get lucky this time. And this time I'm going to have to multiply them both by something. I think I'll get rid of x. I'll make this a 2 and this a 5. I'd like one to be negative so I can add them. So that gives me 6 and negative 20, which is negative 14 for y. And it gives me 60 and negative 80. 60 and negative 80, which is negative 20. So that means y is 20 over 14 positive, which would be 10 over 7. So I think y is 10 over 7. And again, that's not very satisfying. I guess it's not as ugly as the other one. And I'll, at risk of stupidity again, I'm going to stick this back into this one. So then if I took 16 minus 4, you tell me if I'm blowing this, 16 minus 4 times 10 over 7. 4 times 10 divided by 7. Then that would be equal to 2x. And so if I divide that by 2 and have it convert that to a fraction for me, I got 36 over 7. So my point then would be 36 over 7 and 10 over 7 and 0. So there's my point. So what's my line of intersection then? Again, this is barring some dumb mistakes that I might have made. Well, it's 36 over 7, 10 over 7, 0, plus the much more satisfying vector, or much more satisfying answer we just got, which is negative 11, 9, and 14. So the only advantage of the cross product was we got kind of whole numbered answers for those. Now, what I'm not going to take the time to do is go back and graph this, but does it bother you that these two graphs or these two equations of lines are not the same? Does it bother you? Like, isn't there just like one equation for a line?
It's just that one of them has a different scalar, right? Like they're still equal. So
Yeah, I mean there is only one equation, and so yeah, it's kind of this scalar concept, right? Like, so what can I scale and what can I not scale? Like, I'm multiplying by t, right? T is multiplying by everything anyway. So there's a part of me that I'm just thinking out loud here, but there's a part of me that wants to say, well, couldn't I kind of pull the 99 in the denominator out? I don't know. Actually, I want to give you guys a second to think about that. Can you do something that is mathematically acceptable to do to actually show that those are the same? Because at a glance, they do not look the same. Do you agree with me there? I'm thinking, So I'm thinking because remember, t represents every number possible anyway. So if I somehow change that t to be some other number, I can see that I could multiply the vector times anything I want. But the original starting point, it feels like to me like they're not the same starting point, right? But maybe that doesn't matter. What's your thoughts on that? Just give me a second to think about it. It's like if there's a line, there's all kinds of starting points, right? I can start here, I can start here, I can start here, I can start here. So it's not as though that first point is actually the same. I'm not going to get that to look the same. It's just important that both of those points are actually on the line, like they're actually on the plane. In other words, if I plug them into the two original equations that we had back here, they both should say yes. Yes, that x, that y, that z, that really does make it 30. That really does make it 16. So I guess I'm not going to get the first points to look the same. But doesn't the vector need to be pointing the same way? Direction is direction, right? Again, because it's fun, let's just play with this for a second. So my point is, if you took that top vector, which is t, and you said instead of t, I'm going to say 99 times t, isn't that just a scalar multiplier? And so do you agree that that actually doesn't change anything? Again, I'm after conceptual understanding here more than I am procedural understanding. Since t represents every number possible, which is what produces all the points, positive and negative, if I just say times 99, I haven't really changed anything. But then if I distributed that 99 in there, and you can see why I picked 99, 99 divided by 9 is 11. So I have 62 times 11, which is 682. So this becomes t times 682. And then 99 divided by 11 is 9, and 9 times 62 is 558. So this is negative 558. And then the 99s cancel over here, so I get negative 868. Do you agree that's the same? That doesn't change anything. So the question is it actually the same as this? Well, let's see. Is there something I could divide 682 by to get 11? Let's find out. 682 divided by 11 turns out to be, well, 62. That's interesting. So if I divide this by 62 and I divide this by 62, that's what a scalar multiplier is. The question is, will I get all those same numbers that I had above? So what is, so let's see. That gives me 62 divided by 682 divided by 62 gives me positive 11. That's not good because I was supposed to get negative 11. 558 divided by 62 gives me 9, negative 9, but that's not good because I was supposed to get positive 9. And then 868 divided by 62 does indeed give me 14, except for it's negative. So did it work? Did it not work? Well, notice your scalar multiplier is not limited to a positive number. Notice every single sign is wrong, which means if I multiply them by -1. So sure enough, those actually are the same exact line. They have different starting points because there's infinitely many starting points on this line of intersection that I could choose from, but the vector direction, exactly the same. So what's your take? I said at the start of this is the easy way, or the way the book would teach. I think it's cool to realize I could maybe invent this myself, or I could do this in more of a blue collar way, but it's not as though the cross product wasn't a lot of trouble, right? And obviously it's not something to be hard to explain to somebody else. Was that actually any easier? So I think the answer to that is a little bit debatable. What you're going to see if you get stuck on the book problems in this section, when you watch the videos, you're going to see a fairly sterile solution that will be a little bit surprising to you, perhaps, and you'll just either be forced to just do what he said, if you will, and just kind of copy it, or do I trust myself to think? That's kind of the problem. And so it'd be good if you ask me questions about that tomorrow. But let's squeeze in kind of one more quick example here. Third and final example. Distance from a point to a plane. That's interesting. So you are saying if I had some plane out here and there's some point over here in space, do you understand how do you measure that? I mean, I'm sitting at my desk right now, and it's like, how far is this pen from my desk? You can't see it. It's right there. How far is that down? Does it make sense you don't measure that sideways? Like, how do I measure that? How do I measure how far the pen is from the desk? If you measure in whatever angle you want, there's like a million answers. It's 6 feet if I go over there. It's 2 feet if I'm over here. It's 18 inches if I'm right there. What does it mean to be the distance away from? If it's 2 points, it's obvious. If it's between my two fingertips, it's kind of obvious. There's only one choice, but it's different if it's the distance from even, say, a point to a line. That distance is going to go straight at it. In other words, that's what the distance is right there. Perpendicular. Why does that look like a stick man holding something? So the same thing is true for us. If I want to measure this distance, then I'm going to have to kind of head over here and kind of pierce through this, but I'm going to have to hit this in a way that's actually perpendicular to that plane. So again, let's do something stupid here and make up something random and get ourselves in trouble, because it's more fun. X minus 2y plus 3z equals 12. Let's say that might be nice. And I could get unlucky here, right, and accidentally pick a point on the plane. That'd be a bummer. So hopefully that won't happen, but let's pick the point 7, 5. Feels like even numbers might maybe get us something a little nicer. 6, 4, 2. So I could take a second and make sure 6, 4, 2 doesn't equal 12 when I plug it in there, because that'd be a bummer if that happened. Let's see, 6 minus 8 is -2 plus 6. Nope, it's not. So that's good. So how am I going to do that? Any good ideas? Well, notice we always like whenever something is perpendicular. In a sense, this is why this is one of the applications to this, because we kind of like when stuff is perpendicular to a plane, right? Because that's kind of how the whole plane's defined. In other words, if I went over here and kind of, drew in the perpendicular vector to that plane, 1, -2, 3, that's one of the main takeaways from this section. That is perpendicular to the plane. I could just steal that vector straight from its equation. And so that's actually going the correct direction. That's kind of cool. But notice it's not where I want it to be. Remember, all by itself, that vector is emanating from 0, 0, 0. It's not emanating from the point I want it to. If I just draw it there, it's not going to hit 6, 4, 2. So how could I make it hit 6, 4, 2? Well, from what we just learned, that's actually not that hard. If I just say I want the equation to be 6, notice I'm looking at the x's, 6 and 1, 6 plus 1t. Now I'm looking at the y's, 4 and -2, so that'd be 4 minus 2t. And now I'm looking at the z's, 2 plus 3t. Isn't that the equation of the line? And just to make it kind of a cool label out of it, I'll say equation of line AB, and I'll go over here and label this A and this B. If I just take that vector and say, you're going if I take the point 6, 4, 2, and then I say, hey, go every distance possible you want in the direction of 1, -2, 3. So remember, t is in the set of all real numbers. It's negatives, positives, fractions, decimals. If you pick every number possible for t and you plug them in one at a time, you will get all the points. You'll get 1 billion points, and they'll define that line. That's why that works. So that's a vector representation of that line. So I actually have the line now in the correct location. That's kind of cool. But I'm really after the distance. Again, here's some more terminology in math, but if you say AB and you put a segment over the top of it, now you're saying, I don't want the line AB that goes forever. I literally just want that distance of that segment from A to B. This is interesting. Is there some way to find the coordinate for B? Like, where does that line actually hit our plane? How would you do that? Any brilliant ideas?
Is it where each of the coordinates are equal to each other?
What do you mean each of the coordinates? You mean these
Like,
right here?
yeah. Where the
In other words,
sorry,
all,
yeah.
yeah. So all these coordinates, you're saying they're all equal. Like if I put the right number in for t, then I get 7, 7, 7. Is that what you said?
No, where I'm just thinking out loud, but like
Good.
on your plane,
you.
you have that point B on the plane, which is some x, y, z coordinate. Then you have some point along the line of A, which is an x, y, z. And I guess where they're equal, they might intersect.
That's exactly right. In a sense, the point B is the one point that lives on the plane, which means it's a solution to this equation, right? And then that point B also has to be a solution to this. Well, it's not so much an equation, although I guess it is. In other words, I got to find a value for t so that these 3 points, X, Y, and Z, match these 3 points, right? So that's exactly right. Well, how do I do that? Well, just like before, algebraically, I've got to kind of put them together somehow. Well, isn't this a representation for X? And isn't that a representation for Y? And isn't that a representation for Z? So couldn't I just throw those in up here? Why would that be cool to do that algebraically? What's good about that?
And you've got one equation, one unknown. You can
Got
solve.
one equation, one unknown. Couldn't be said any better. So 4 minus 2t is to be replaced with y, since the y coordinate of our line is 4 minus 2t. And the equation of the plane says plus 3 times z, but we said z is 2 plus 3t. And I need that all to equal 12. And so if I could find that t, then I would know what t, and I would know the coordinates of that point. So that's kind of fun. Let's see if it works out. So I get 6 plus t minus 2 times 4 minus 2 times minus 2t plus 3 times 2 is 6 plus 3 times 3 is 9. So I get a grand total of 5 t's. That's not good. I get 14 t's. And I get 6 minus 8 is -2 plus 6 is 4, I believe. And so we're well on our way now. So I get 14t equals 12 minus 4, which is 8. And again, I don't get a nice whole number. I get 8 over 14, which is 4 over 7. So I get sort of a t of 4 over 7. And so again, this feels like a non-book problem, like somebody didn't put any thought into making this work out nice. So if I plug that in for t, I'm literally going to have the coordinates of this point. So b, then I could say, and I'm just going to write this as decimals. Well, maybe I'll write it as a fraction. So b is equal to, well, 6 plus t, right? So if I say 6 plus 4 divided by 7, and just to make it a little nicer looking of a fraction, I'll just write it as a single fraction, 46 over 7. And 4 minus 2t, 4 minus 2 times 4 over 7. I get 20 over 7 for that. And lastly, I get 2 plus 3t, so 2 plus 3 times 4 divided by 7. Convert that to a fraction, I get 26 over 7. And so they're all in the sevenths. And so it's kind of good to see that, yeah, sure enough, that t is in the set of the real numbers, because it didn't work out real nice. It's not some nice, cool answer. You're led to believe in book assignments that things just work out nice. Well, they don't. So I have that coordinate now, but how do I find the distance between the 2 points A and B now that I have a coordinate for it? You should be thinking Pythagorean theorem. How do you find the distance between a couple of points? I'm going to erase this, but we have just enough time to say this. But if it was in 2 dimensions, and you wanted to know that distance, because the 2 points are probably not lined up vertically or horizontally, that creates a hypotenuse. And although the hypotenuse is a weird distance, those x's and y's will not be. And you may remember that if you take the x coordinate of this, which is say 5, and the x coordinate of this, which is say 1, then since I went over 1 to get here and I went over 5 to get there, then wouldn't I go 5 minus 1, which is 4? I mean, isn't that the distance of that? We go x minus x. That's how we get that distance. And the same with y. If this was a distance of like up 6 and this was a distance of up 3, then that means to get to this point I went up 3, to get to this point I went up 6. And so if I subtract those two, 6 minus 3, then I get that. So I got to subtract the x's, right? That's how we found the slope. That's how we found the distance of something. And then I'd square those and add them together and square root them. Well, that works in 3D, as you've been saying, as we've been seeing. So that means sort of and again, what you'd see in a video for this would just be somebody saying, now use the distance formula. The question is, did you understand that deeply enough a bunch of terms ago when you saw it that you see it here? Or is it just kind of a formula that you plug things into that you don't really have a sense of why it works? It's not the distance formula, it's just Pythagorean theorem. So if and I'm just going to type this whole mess into my calculator and get a decimal answer to this just to save a little bit of time, but basically then the distance AB would be equal to the square root of the difference between all of those numbers. So I'll write, and it doesn't matter which way I subtract, I like whole numbers, so I guess I'm going to subtract that way, because remember, you're going to square this anyway. So 46 over 7, I'm going to square that, and I'm going to add that to 4 minus 20 over 7, and square that. I'm going to add that to 2 minus 26 over 7 and square that. And then I'll get my answer. So I'm going to type that whole mess in really quick and we'll be done. 46 divided by 7. I say square that number plus, maybe we'll get lucky and this will turn out really nice, but I doubt it. 20 divided by 7, square that. So I'm not typing the square root just yet. I'm actually saying I'm typing just the parenthesis part without the square root. 4 minus 20 over 7 plus 2 minus 26 over 7. Square that and get some horrific decimal. Maybe I'll get lucky and it'll convert to a fraction pretty nice. That actually did. And so this is the square root of 32 over 7, which is approximately 2.14. So that's how far apart, that's how far away. So that point was pretty close, I guess you could say, to the plane. Again, I did a lot of math just now. It was easy math, but all I got to do is type one thing wrong in. I'm very merciful on tests for dumb mistakes. I sort of have to be, don't I? Because I make a lot of them, but I got to be able to see. I got to be able to see what you wrote, got to see what you were doing. And I can't tell if you typed it into your calculator wrong. I'm double checking to make sure I actually typed what I think I typed. I think I'm okay. So as usual, we're over time here, but it will only take a second. Take off if you need to, and I'm just going to take a quick pic of this, and I want to go graph this and see if 2.14 looks at least reasonable. This won't take very long to graph, so why not? Delete, delete, delete. So I've got my plane, which was x minus 2y plus 3z, x minus 2y plus 3z equals 12. So there's my plane. That's really cool. Now I go graph my point, 6, 4, 2, 6, 4, 2. Close that parenthesis off. Boom. Now you have a scale in front of you as to what 2 is, right? Because notice it's marked out 2, 4, 6, 8. So it's basically the distance between two of those tick marks. And that looks pretty reasonable, doesn't it? Doesn't that look like actually a hair over the distance between, say, 6 and 8 on the z-axis? Doesn't that look a hair over the distance right there? So now I'm thinking I didn't make any mistakes for the first time. Before that, I'm thinking I'm almost guaranteed to have made some kind of a mistake. I'm sure, and I haven't played with this, but I'm sure there's a command in here where I could actually also graph the point where it hit. Remember, we found at t, when a certain value t, we found the coordinates of the point where it actually hit the graph. And I bet you I could go in there and say, what's the distance between those? And it might tell me that. So I could even maybe check it a little bit in more detail. But what you're going to find, and I'll just say this kind of going out the door, there's an amazing shortcut for this question. We just did this entirely based on, well, we did it blue collar style. But you'll see, and I'll leave you to do this, but the video has an amazingly cool, for this question, has an amazingly cool shortcut for this. And no explanation is given for it. I had to play with it a little bit to kind of go, you know, when I've learned this stuff, to kind of go, what? Where in the world does that come from? But definitely watch that. But his explanation will be completely different, and it has to do with finding a point. Again, feel free to leave if you need to, but I guess I'll just say this since we're talking about it. We'll call that good. So the cool shortcut for this takes into account the projection. Remember that whole formula we had where we looked at the projection of U onto V? You may remember what did that do if this was V down here and we had U up here? The projection of U onto V was ... taking that down, like that's it. That's the projection of U onto V right there. And in a sense, what that produces is, well, this distance right here. In other words, that distance right there, that's the distance we were after just now, right? If you think of the tip of this U up here being the point out in space and the V being the plane down below, it's really that distance right there that we needed. And so there's kind of a neat formula for this that you can use. It amounts to, though, having to find some point, and I'll just say this quickly, but it's like you have to find some point on the plane. And remember, it's really easy to find a point on a plane. Pick X and Y to be 0. It's really quick to find a point on a plane. If you stare at that equation right there and I said, okay, X and Y are 0. All right, well then Z is 4. So there's a point on the plane, 0, 0, 4. Can you see that point on this plane, by the way? 0, 0, 4. Yeah, that's where it's hitting. It's hitting actually right there. So you have to find some other point on the plane. And then you're going to think of the plane as one of the vectors, if you will. And then you're going to create this vector right here. And then you're going to kind of use that projection. So again, what this does is it's interesting. I tend personally toward blue collar approaches. Like I understand that it makes sense. If it takes me a little more time, then I'm okay with that because I understand what I'm doing. If you give me a shortcut, I love shortcuts, but I don't find myself wanting to use them unless I can actually own the formula, even create the formula for myself that produces it. Understand it. When I just did that with distance formula to you, it wasn't a formula to me. It was like, oh, it's just Pythagorean theorem. I understand where it comes from. I used it. I used that formula, but that's because I own it. I didn't borrow it from somebody. I didn't borrow it because the example in the book showed it, and then I just copied it and got the problem right, but I have no idea what I'm doing. I owned it. So you will find that his explanation as to the formula that involves projection, you're not going to understand what it is. It's not even the same as the formula that I gave you. It's like a modification of it. So anyway, it's just interesting. I got to shut up. All right. Get out of here. Have a good day.
All right. Thanks, Doug.
Thank you, Doug.
Thank you all. See you tomorrow.
I actually had a question about that line. at the intersection of two planes.
Mm-hmm.
When I followed along and put it into GeoGebra, I think I might have messed up my planes or my point B because it doesn't go through their intersection. I can share my screen.
Yeah. Do it. You already have the power, right? I don't think I have to give that to you. I just have to unshare.
Oh. I think my planes might be where I went wrong. But
So 5, 5, 3, 2, 30, 2, 4, negative 1, 16. And we said A was 0. B was so B, C is B minus A. B. So B was not, I think B isn't right. Wait. Yeah, so your B is already the vector.
oh, this is the line or the vector.
That's already the vector. That was A minus B.
Okay. Okay, that's what it is then. So then if I do this,
So you should, yeah, correct.
okay. And I noticed that GeoGebra doesn't like the parentheses because if I put it this way, then it seems to think T is some kind of command.
Isn't it weird? Like it just isn't, it's not super intuitive.
Yeah.
It gets mad easily, and then it kind of doesn't tell you what's wrong either.
Okay. Yeah, that answers my questions about that. I was also a little confused about the distance formula that you used because I know it's kind of based on the right triangle trig Pythagorean theorem stuff, but I was confused because we didn't really have a leg or a base.
Yeah, let me show what I mean. So are you good with the fact that if you go x minus x, you're going to get the x distance?
Yes.
Okay, so stare at this for a second. So if this is the z-axis and this is the x-axis, this is the y-axis. And so let's go to a point in space now. So I'm going to go to the point x is 1, 2, 3, 4, 5, 6. And then I'm going to go y is 1, 2. So I'm at the point 6, 2. And then to make this look nice, I'm going to go up 1, 2, 3, 4, 5. So would you agree that's about right there?
Yeah.
So there's my final point. And so what I'd like to know in this case, just to make it easy, what I'd like to know is that distance right there. Now, again, that's very confusing to look at, right? If you don't know how I got there, but to get there, didn't I go 6 and then 2?
Yeah,
So
I see now.
6 there, 2 there. But the point is that on the flat ground, that's a right triangle right there.
Yeah, that makes sense.
And then I went up from there, but that's very hard to visualize. But can you tell that's actually a right triangle?
Yeah.
So in the end, if I go the square root of 6 squared plus 2 squared, I get the distance down here of the square root of 40. That's that there, but that's not a hypotenuse. That's the leg. Like the hypotenuse of the XY plane triangle is the square root of 40. And then this was a height of 5. And so now I'm going to square 40, square the square root of 40, and then square 5, and then add them together and square root it. So the end result is you're really squaring 2, 6, and 5, adding them all together and square rooting it, because it's really 2 right triangles that it took to produce that distance.
Okay. Yeah, that makes sense. I guess I was just having trouble visualizing it without that 3D angle.
Mhm. Yeah, it's kind of legit, isn't it?
Okay. Thank you.
See you tomorrow.
See you tomorrow.